Okay, so this is another AP Physics FRQ 2024 course video. Today we'll be doing rotations. Okay, so read this problem, read the context, and we'll start. Okay, we'll start. Alright, so we read that the following rectangle represents figure 1 right here. On the rectangle, draw and label the forces, not the components, exerting on the beam. Draw the forces as a distinct arrow starting. It says distinct arrow, so we might have to be accurate on size, maybe. Distinct arrow, I think we just have to draw and label them. Yeah. Pointing away from the point at which the force is exerted, but I think it means if there's a force going down, we should draw it going down. I think that's what I mean by pointing away. Let's look at not yet. Okay, so let's see. So we first know that there's tension going that way, and we also know there's the weight of the beam going down. But you may see that since it says the beam remains horizontal, this suggests that it's at equilibrium. And if we notice that if we draw the components of tension, we notice that there's actually a force pressing down, but that would also imply that there's a force pushing up this way too. But I also do believe that this hinge also has a component upwards as well. That helps with, yeah, so the hinge, or whatever it's called in rotation, I forgot, it also has a force. Not only do we know that it must counteract this force, but the force also counteracts the rotational force right here that rotates it. So therefore this, I mean, it's not really given, it's hard to explain, but just know that there are component forces for this hinge. So we just have to write like this, draw like that. This is FH for the hinge. And then we have the tension right here, T. Then we got FG. So I'll tell you a story that I did not read this part when I did the FRQ, and so I did not include this FH into my diagram, and I probably lost points on that, but also, the reason why it's pointing this way, I believe, not only is it to counteract this, but also, if it wasn't a hinge and there was just a wall right here, and the tension force was going right here, I'm pretty sure they would have, I'm sure the FT would definitely rotate, or would be unstable. So, because I mean, yeah, like just think about it logically. If you have a beam and a wall right next to it without the hinge, you just have a string that's actually pulling. I don't think the weight of this thing, if like, it just doesn't make sense that there would be a string to even hold up the thing with a hinge, unless the hinge actually did have force opposing the FG. Alright, so all you have to do is draw these three lines, don't draw the components, you know. Yeah. Alright, so reviewing the answers. Okay, so string is then lower, so we now have a theta that is also less, so this is theta 1, so that would mean theta 2 is less than theta 1. So let's think about it. So you have a lower string, right? So Ft equals, so we draw the components like this, or yeah, like that, based on the angle. This way, it's bad to draw. And Ft is the hypotenuse. Ft2 should, okay, so Ft1 is this triangle. So this is my type of font. So review the FRQ to see how to get your points. So just thinking about it, if you ever tried doing something similar, you would naturally think, and it is right, that pulling the string down will cause more tension in the string, and that's because of torque, and because the vertical thing was holding up the the main purpose of the vertical component was to hold up the gravity, but as it decreases, this vertical part decreases in value, but this side, this component, the horizontal, increases because this decreases. It's like sine and cosine. And you know the equation, you write Ft sine theta equals torque. And remember that they're still both in equilibrium, so this torque still has to be the same torque in order to keep equilibrium. So because of that, Ft is equal to torque over sine theta. And as we know, sine theta decreases as the angle decreases. And since this angle is less than angle 1, that would mean that the Ft should increase as sine theta's theta angle decreases. So it should be this one, and you should write, it says justify, using qualitative reasoning, I don't know what qualitative reasoning behind that is, but we'll just write, to keep the system in equilibrium, the torque must stay the same, and therefore the tension must increase due to the change in angle and decreasing value of the vertical component because of a smaller angle. Therefore, smaller angle causes the force tension to increase to keep equilibrium as the angle decreases. and probably just restate because theta 2 is less than theta 1, ft2 is greater than ft1. And this is the explanation for this. It's a lot better than what I wrote. So in order for the beam to remain horizontal and at equilibrium, the torque must be exerted the string the same for all angles. When the angle decreases, the perpendicular component remains the same. Therefore, the tension perpendicular. I don't know what that was talking about. Therefore, the tension must be greater than the angle. I don't get what it means by perpendicular. If it's referring to the vertical, but I mean, look at the guideline. It says relating the vertical component of the string about weight of the bar and relating the force needed to exert. So yeah, it's basically saying if the vertical component gets smaller and smaller due to the angle, the tension itself needs to increase to compensate for the lack of vertical component. So this vertical component will decrease if the ft and this ft, ft2 is equal to ft1. But since ft2 is greater than ft1, it will cause this side to stay in equilibrium. That's basically it. I mean, just look at the equation, torque over sine theta. You can just explain it more conceptually like that. Starting with Newton's second law in rotational form, which is torque equals torque. I mean, there's actually a lot of equations for it. It is this or MA. It was MAR. Wait, let me check. Yeah, it was MAR sine theta. So those two came into mind when he said that. So let's see. To write an expression of magnitude of tension to string, express your answers in terms of m theta. Okay, so we're using this one. Using this definition. So this is going to appropriate blah blah blah. So we're going to start with torque 1 plus torque 2, or actually minus torque 2, equals don't use acceleration for this. I think acceleration might actually be actually no, it's equal to 0, my bad. It's equal to 0. Okay, and then ft, and ft is positive because it's going counterclockwise, while the gravity torque is going clockwise, so the minus sign is gravity. ft sine theta r. Wait, I forgot there's an r here, but if r was consistent or whatever, it's fine. And r is the distance from the force to the hinge, by the way. Minus, let's just write r1. Actually, no. We're gonna write r. We already have a variable for it. Like, yeah, this is gonna be L. It's gonna be L. And the reason why it's L is because the tension is from here, and the force is 1 L away from the tension force right here. It's this force that counteracts this force, so it has to be a vertical force that's the rotational force, or rotational component, whatever. So since it starts from here, and I made a mistake of drawing my tension force here and here, so I wrote tan theta, which was really bad. Anyways, minus mg sin theta. And for the force of gravity is at its center of mass, which we're gonna assume is, it is evenly balanced, right? Is that evenly balanced? Uniform beam, yeah, so it's evenly balanced, so the mass is half of L and 1/2 L. And we're gonna set them equal, right? Wait, let me see. No, I don't think there's a, hold on. Alright, so with this being equal, let's find theta, because this theta is, sine theta is solvable because it is 90 degrees from here. Yeah, the force and the bar are 90 degrees. So so this is gonna be 90 degrees, which is just 1. And those L's cancel out, and we solve for ft, so ft equals m, capital M, because that's what they wanted to be, g as a constant of acceleration on Earth, due to gravity, and divide by sine theta. And there's a 2 for that one out. So that's the answer for that. Remember that it is the distance of the bar to the hinge, or the force to the hinge, and the angle is based on the force vector, which is this vector, and that vector, to the actual bar, not the hinge, it's the actual bar. So there you go. So I think just writing torque equals, or summation of torque first, equals 0 is your first point, and then going through it. Let's see. Torque net equals 0, okay, we got that. Yeah. Magnitude of the torque string, we got that. And correct answer, so we got 3 points. We got 3 points. Next one. Is your derived equation consistent with your custom? Well, I mean, I did justify my thing with the equation, so I'm not gonna explain it, but I might just type something down. Yes, because as theta decreases, sine theta also decreases. But because force tension is inversely proportional to sine theta, as sine theta decreases, force tension should increase. There you go. I don't know if I have to write more or okay, let's see example. 1.4 an attempt at dependence. Wait. Function what? I don't know what that means. Okay, so for its use functional dependency related to the okay, whatever. Again, because shows from tension from theta 90 decreases as the tension will be on an angle. Yeah, about the same wording. I should have wrote the interval theta less than 90 degrees. Let the string and the beam begins to rotate around the hinge of the blah 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 blah. Sketch the angular speed of the beam. So, yeah, so I think that the rotational force should be consistent, so that would mean, wait, no, it's saying what's the rotational force, omega, and because it's no longer in equilibrium, and in fact, it's equal to mg, mg, since the force is perpendicular, that's just one half L, before it becomes vertical, so it's gonna move, and then it's gonna stop before it becomes like this, so I think we're gonna have to use rotational kinematic, energy, and we can write that, what is this? Let's just say this is arbitrary height of h, or actually no, it's gonna follow length L, right? Yeah, it should follow length L. So L, mgh is lgi equals 1/2 I omega squared, and these cancel out, and you're given the equation lg, okay, lg 2 times lg equals omega. Yeah, so, oh, but the thing is, L is, actually, yeah, I'll just write L as the function, so. There's a new class of blockbuster drugs. It should be around like this, but there is. So, when it says before it turns vertical is its max speed, so the speed is when it's at exactly vertical. It will be basically almost at its max speed when it's vertical. So, the thing is because it's at its max speed when it's vertical, when it goes upwards, it's going to decrease in value. So, as it's going to speed up, and then slowly, but it's going to cap at here, and then speed down. So the value should be like starting from 0, should be, and it says before it so it should be something like that. Let's see. Yeah. Because let's see, yeah, it's somewhat like that. But this doesn't account for the fact that it's gonna decrease in speed afterwards. After it goes over its hinge, it's gonna actually decrease in value. So let's see. Concave downwards and monotonically decreasing. I don't know what that means. Yeah, so it's gonna have that slight curve to it, like it looks like this. Maybe a slight ish. Yeah, it just looks around the same. And it's gonna reach around its peak around there, so yeah. I think that's the last question, yeah. There you go. Yallah.